How's it going, everyone? So the purpose of this video is to go over two specific problems from this week's module, and I hope they help. I'm going to be using, what's it called? The One Page, which is a really cool place where I can write stuff out. So instead of me having the old camera, I can just write things digitally, but it's a little bit hard with what I have, but I really hope it doesn't look too bad. So with that being said, let's jump into it. So first and foremost, I got to share the screen, which is right here. The first problem we're going to be working on is a more basic one that covers the fundamentals of momentum. So first and foremost, we already know momentum is mass times velocity. Um, but how to apply that into specific problems is the real question. So let's read this problem and let's figure out how to solve it. So first problem, object 1 has a mass of 4.37 kilograms and is moving to the right 31.1 meters per second. Object 2 has a mass of 16.2 kilograms and is also moving to the right. How fast in meters per second must object 2 be moving in order for it to have the same momentum as object 1? So for this problem, you don't have to worry about conservation of momentum, which is a really big principle for this chapter. This one's kind of building you up to understanding first momentum and explicitly more like how to um, quantify the way they're trying to word this problem. So what they're trying to get you to do is in the second sentence, how fast in meters per second must object 2 be moving in order for it to have the same momentum as object 1? So what this means is that object 2 has, so I'm going to put P for object 2. So as you can see here, mass 1, mass 2, momentum 2 represents this one right here. So P2 being the momentum for mass 2, they're saying that they want us to figure out what is that momentum if P2 has the same momentum as P1. So these two right there. So we don't know the velocity for the second mass, but we do know it for the first one. We know the masses for both of them. So we can just define what momentum is. For P2, it's mass 2 times velocity 2. So as you can see in the little diagram I've already defined everything just to get that out of the way. Just using the same the notation is really useful. Okay, we're going to make that equal to the definition of momentum 1, which is mass 1 times v1. Okay, so you can kind of see now, all we're going to do now is plug in our values into there. And all we have to do is find out what the velocity is for momentum 2. So this thing, we're trying to figure this out. This V2. So to do that, it's a little bit of just math. If we plug in the mass for the bigger object, it turns out to be 16.2 kilograms. The velocity, we don't know, that's what we're trying to solve for. And that is equal to the mass of the the smaller mass, which is 4.37 kilograms times, let me move this a little bit this way, times the velocity, which is 31.1 meters per second. Okay, so from here you can see where we're going to go. We're essentially going to divide 16.2 kilograms to the other side so we can solve for the velocity of the second object. And so that's pretty much the basis for this problem. We're not trying to find any type of conservation. We're just simply trying to find that velocity with a specific constraint where the momentums of the two objects have to equal. Since the dependency of momentum relies on the mass and the velocity, we can do this to figure that out. Okay. So before we get on to the other problem, I want to just make a problem up that can segue us to that last problem, because the last problem jumps a few more hurdles. And I want to do a problem with conservation of momentum now. So I didn't actually plan for this. I just want to do it now. So hopefully this thing doesn't give me any problems. Okay, let's call this problem 2. So problem 2, I'm just gonna draw this out here. So we have two objects. Excuse my really beautiful rectangle right there. So we have mass 1 and mass 2. Okay. If we say that mass 2 is, or mass 1, let's say mass 1 is 10 kilograms and mass 2 is 15. And I know what the velocities are for both of these objects. So velocity 1, let's say 5 meters per second. But now we're going to change this up a little bit. This is going to be really useful in understanding the fact that momentum is a vector. So that means it has direction. And if it points in one specific direction, knowing how to differentiate that. So this is why I wanted to do this problem. Velocity for mass 2, let's say it's 6 meters per second. But so let me just backtrack a little bit. The velocity for the first mass points to the right. The velocity for the second mass points to the left. So if we have these two objects pointing in opposite directions, and we know once that collision happens, I'm going to say that collision is elastic. So you're going to hear two different terms, elastic and inelastic. Inelastic means, so inelastic means that when objects collide, they're going to stick together. Elastic means they will bounce off of each other. So there's a purpose to this. For this one, we're going to say inelastic. So that means they're not going to stick together. So let's put elastic collision. Okay. I mean, I didn't have to write it, but I did. Because I'm so slow at writing with this. So this is the first scenario right here. I'm going to put a 1 right there. Second scenario is after they collide. After they collide, the problem tells us, so here we go. They're colliding with each other, but they don't stick to each other. Instead, what happens is they tell you that the velocity for the first mass, so now I'm going to call this V1 prime. Excuse the terrible. Let me try to redo that. Now that looks like a Y. Let's do V1 prime. Well, that works. Let's say the velocity for V1 prime. So this is a new velocity after the collision for the first mass. Let's say the velocity is 4 meters per second. And the velocity is pointing in the opposite direction at which it was coming in at the beginning. So keep that in mind. And now velocity 2 prime is unknown. So the problem is going to ask us to find this velocity. How do we do that? That's the big situation here. So we're going to call this scenario 2. And now we're going to zoom out a little bit. And we're going to move a little to this side right there. Okay. So this calls into play something called conservation of momentum. We want to find all the momentums in the first scenario and then find all the momentums in the second one. And because momentum has to conserve, the first scenario's momentums have to equal to the second scenario's momentum. So to put that into math terms, let's write it out. For the first one, I'm not going to write the values yet. I'm just going to write the variables for them. So we have mass 1. We already know what momentum is equal to, is mass times velocity. So I'm just writing the values. So m1, v1, that's the momentum for the first object. Here's the thing. Because we have momentum pointing in different directions, we have to indicate a positive direction. So I'm going to use red just to indicate that this direction is positive. You can choose the other way. It will give you the same answer. But I just want to be explicit with this because this is a really vital point to getting the right answer. So we have the momentum for the first one, and it's positive because it's pointing in the same direction as the positive direction indicator. But now for the second momentum, it's pointing in the opposite direction. So we have to make sure to include a negative sign for that. If not, we're going to get it wrong. So now I'm going to put minus and put the momentum for the second object. M2, V2. There we go. That's it. There's only these two momentums. There's no third object. If there was, you'd add a third term for that object. So there's only two. Here you go. Okay, let's box this up. This is the initial momentum for the total system in the first scenario. Now going on to the second one, I'm going to write mass 1, V1 prime. And here is the situation. The velocity is not pointing in the same direction as a positive direction. So we have to make sure to make this momentum negative key here. So add a negative sign. Okay. The second one, we do not know what it is. We don't know if that mass will go to the right or to the left. So the way to do these problems is to make it neutral. You're just going to write the momentum as positive, M2, V2 prime. And if it turns out that your answer is negative, that tells us that the mass was actually going in the opposite direction and not in the positive direction. So that's how you'll get the indication for that. You always want to assume the mass is, the momentum is positive. And if you end up getting an answer with a negative sign, that means it was supposed to go the other way. And that helps clarify where it's going, plus the magnitude. Okay, so we have these two. And with the conservation of momentum, we know that all of this, both of these scenarios have to equal to each other. So let's write it down here. M1, V1 minus M2, V2. That has to equal to the second scenario, negative M1, V1 prime. Remember, I'm calling it prime because it's a different velocity. It doesn't equal V1. It's a totally different value. In this case, it's 4, and V1 is 5. So that is why I'm doing the prime. It's just to differentiate them. Here we go. So we have everything. We know the mass for all of these. We know the velocity for V1, V2, V1 prime. And what we're trying to solve for is this right here. So it's pretty much just plugging it in and doing a little bit of math. And sometimes the math is what gets us lost with these problems. So we have to make sure to not just not care about solving it, just like going through it quickly, like take your time. It will pay off at the end. So the values for M1, I'm not going to plug them all in. I'm just going to start moving things around. So the first thing I want to do is subtract this term or add this term to both sides. M1, V1 prime. M1, V1 prime. And what we get is three terms on this side now. M1, V1 plus M1, V1 prime minus M2, V2 is equal to M2, V2 prime. Okay, because we're trying to solve for that. So because we're trying to solve for that, we are going to divide the mass to isolate that. M2. So now this cancels out and we're left with this term. V2 prime gives us this right here. All you have to do now is plug in your values in there and you will get an answer for V2 prime. So I'm going to leave it at that for this problem. You just have to plug in your values. You do not want to include any more negative signs or anything. That was all included. All you're doing is putting the magnitudes for everything. masses don't have a direction, so you don't have to worry about that. But when it comes to the velocities, for V1, you're going to input 5. For V1 prime, you're just going to put 4. You're not going to include anything else. For V2, you're going to put 6 meters per second. So that's how you do it. You already included the direction from the beginning. So you never have to include anything else. Because sometimes double negatives is what causes these problems to go haywire.